Hello, I'm Philip Muggleston, and in this series of videos we're covering the predictive capabilities native to SAP HANA. In this video we're going to look at logistic regression. Now, logistic regression is a little bit different. In fact, it allows us to create true or false or yes/no outcomes. So it can be useful in fraud detection or credit scoring. Or in our example, we're going to look at identifying gender, for example, based on the amount of spend. So the dependent axis basically has a value typically of yes or no, true or false, or male and female. And the explanatory variables can be any numeric variables that we are typically used to seeing. So for example, we might want to put spend as our explanatory variable, and we might want to have gender as our dependent variable. So what does the curve look like? Well, basically, it looks something a little bit like this in many cases. And what you can see is that basically the values fall into one or two halves. So if we were to draw just a little line across showing us about where the half is, okay, it should be a little bit lower than that, then we can see, for example, if the gender was male, it might be up here, the gender was female, or true and false, depending on your case, might be below here. So that basically is how logistic regression works. You can use the value of spend and try to identify, for example, whether it's male or female, or whether it's fraudulent or not, or whether you should or not give someone credit. For our logistic regression example, we're going to work with a slightly different data set. Now, what we can see here, we have a customer data set where we have about 200,000 different customers, but we're just looking at the first 200 rows here. And what we can see is we've got for each customer the gender, which is 0 or 1, depending on whether they're male or female. And if we were to just have a quick analysis of the data set, looking, for example, at gender, we can see we've got quite a lot of values and a fairly even distribution. So we've got male and female in our customer data. And then in terms of how we're going to try to predict the customer's gender, we can, to understand our customers better, we can actually look at the sales amounts. We've got all the transactions performed by each customer, and we can see the actual sales amount. So if we were to sum the sales amount over time, we'd get total sales, or for the most recent month, then we could get maybe the recent spend or the recent quarter. So those are the figures that we're going to be using in this example. So let's go and have a look at the code. Now, the code is a little bit different to what we've seen before, so you really do need to pay attention. In particular, the input data, the order is reversed from what we're used to. So our dependent variable is what is known as gender in this case. It comes second or at the end of the list. And the explanatory variables, the input variables we're going to have, they come at the start of the list. And there's no requirement to have an ID column. So it's a little bit different the way the data is structured when using this algorithm. We have PMML output, we get the equation, so the coefficient table. Again, we use parameters as always. When we use the wrapper generator to create the procedure, we would need to use logistic as the prefix. So that allows us to call the logistic regression algorithm. Now, in the case of our example, I was just showing you that we have order facts where we have sales amount by customer. So what I've done here to create our input data is I've actually summarized or aggregated the sales amount for all of the history of each customer from our fact table, calling that lifetime spend. And then I join that on to the customer data. So for each customer, we get their life spend value. And I've also taken the customer gender ID. That gives us that 10, this Boolean value of whether the customer is male or female. So this is what we're going to use to train our model. And I've just, for the purposes of this example, picked the first 1,000 customers to make it easier for us to view. In terms of the parameters, there are a number of different parameters available with logistic regression. Of course, we have the thread number, and for this we recommend actually to use 4 or more threads if you can. Because the way logistic regression works involves iterating, there are some parameters that you may have seen, for example, from k-means or other algorithms, such as the max number of iterations to perform, because it's iterating around, and when to exit the iterations, so the exit threshold. So we see these two values where you can set a value that makes sense to you. And again, we have the variable num, and this works the same way as we've seen before with bivariate and multivariate regression. So in this case, it's a bivariate, or we have a single explanatory variable. So we're going to set the variable number to 1. And also for logistic regression, we have something known as the method. Now method 0, you'll find more details on this in the manual. Method 0 is the Newton iteration, and that's what we would recommend to use. However, the logistic regression in the PAL also allows us a stochastic gradient ascent, and if you're not really familiar with what that is, I would certainly not recommend that you use it. And it has some additional parameters as well, such as step size if you're using that different method. But the Newtonian iteration, method 0, is what we recommend. So that's the one that we've set for default in this example. Okay, so we've now looked at the code, we've created our source data, we've set up the parameter table, we run the wrapper generator, and then we can go off and build our model. So let's go and run this code. And again, even on a very large volume of data, we actually have about 1 million sales transactions here, and we have 200,000 customers, yet it runs very, very quickly with HANA because it's all running in memory. So we've now built that model. So if we were to refresh our tables, we can see that we've got the coefficient table, which we're used to seeing, and you can see we've got the base coefficient followed by the coefficient for our explanatory variable, which is total spend. So we can see how that equation fits together. And if we want, we can see our model, for example, in PMML. That's an option if we want to store the model itself in PMML. So we see those values, the intercepts, the coefficients, etc. in the PMML. So having done that, we've now built our model. What we also would want to do is try to predict something with it. So see if we can identify what the gender would be based on a certain amount of total spend. Obviously, this is a simple example. So we need to use the wrapper generator again to make a prediction procedure. So for that one, we use forecast with, as always, with the PAL, but this time we're going to say logistic R, so logistic regression. So forecast with logistic R in our wrapper generator. We give it the input data using lifetime spend, which is our single explanatory variable. We give an ID to the data as well, and then off we go and run the prediction using that. And in this example, I've just set up 5 new values to be predicted to see for these different values of lifetime spend whether we think from our model they're likely to be male or female customers, maybe to help us target our customers better in the future. So let's run that. Okay, so it runs very, very quickly. It's applied the equation to our model, and then if we're to refresh the tables we've got, and we can see now we have at the bottom we have a predicted table which has got our results in it. We can see that for each of these 5 values, the gender that's predicted is in fact 1, which would be male in our case. So for those 5 values that we specified, the gender predicted would be male. So that's a simple example of how we can use logistic regression with HANA. In the next video, we're going to look at doing something slightly more complex. We're going to do a multivariate or effective or multiple logistic regression because we'll have more than one explanatory variable.